Anyway, what I'm doing here first is it's a brief introduction into plastic waste recycling. But anyway, let's just get right into it. Looking at the fate of all plastics from the 1950s onwards, the take-home message is that only around 9% of the global plastic waste was recycled. 12% was incinerated and nearly 80% accumulated in landfills or the natural environment. So there is massive scope to increase recycling. Pictures just as these or worse of plastic pollution you may have seen, and you may have also heard of plastic pollution, which is also not good for anybody. So we do need to come up with solutions. Very often Europe presents itself as a leader in recycling of plastics, but it depends a bit what you count as recycling. In 2014, for instance, export of plastic waste to Asia, mostly China, counted as recycling, although in practice this was often not the case. This Chinese recycling route was suddenly closed in December 2017 when China banned the import of plastic waste. Moreover, we cannot legally export these wastes anymore. In May 2019, the EU, with most other countries in the world, the US is a notable exception to that rule, signed a treaty which classifies plastic waste as hazardous. Now, this greatly reduces the legal export of plastic waste to other countries and hence requiring treatment at home. And the receiving states, they've also realized that they don't actually want this waste either, as these plastics are often not recyclable, being contaminated with other wastes. For instance, in 2019, Malaysia sent back a number of waste containers. And this here, right, as shown on this slide, is just one example. So what can we do with plastic waste if we don't want to landfill it? Incineration is always an option. At least it gets the heat back. Another option is to pyrolyze the plastic waste and turn it back into oil. At a temperature of 450 degrees Celsius, polypropylene, for instance, converts into waxes, a small amount of oil, gases, methane, propane, etc., and carbon, as shown here. The chemistry of plastic pyrolysis is well established. There are thousands of papers stating more or less the same. There are quite a number of plastics and they all behave differently when pyrolyzed. Again, taking polypropylene, PP, the chemistry is not as random as one might think. The temperature has a major influence, controlling the amount of waxes, oil and gases as shown in the table here. In general, the higher the pyrolysis temperature, the lower the amount of waxes or oil, and the higher the amount of gases such as methane, propane, etc. I need to introduce two more terms. They are direct and indirect heating. There are two methods of cooking a breakfast egg. Method one, shown here, is what we all do. This is called direct heat transfer. That is, the material is in intimate contact with the heat transfer medium. In this case, well, it's boiling water. Method two is virtually what everybody does in pyrolysis. This method places the egg onto a hot plate and waits for it to cook. This is called indirect heat transfer. Of course, you can improve things by turning the egg. Another word for such a process is rotary kiln reactor. Such reactors are heating from the sides and the heat has difficulties to get in. The result are long residence times, temperature variations within the kiln, and secondary reactions such as cracking. So quite a number of things work against you when recycling plastic wastes in rotary kilns. All right, now moving quickly on to my company. In an earlier talk, I have already explained how we recycle tires, but we can do more. Here, I am going to show you how we recycle plastic wastes, especially mixed plastic wastes, and aluminium laminated plastics. Mixed plastic wastes is a composite plastic, or composite waste. It's a composite waste, and is therefore difficult to recycle. Mixed plastic waste is a composite waste as different plastics are mixed. Ideally, this plastic stream should be remelted and reused. But there is a problem. Never mind that plastics can only be remelted 4 or 5 times. This is as every time remelting occurs, the plastic chain molecules get shorter. You can't remelt mixed plastic waste as the melting temperatures of each plastic is different. But you could pyrolyze the whole lot. Pyrolyzing mixed plastic waste results in different products. Nearly all of the polypropylene converts into waxes, while other plastics will convert to the oil, waxes, gases, and carbon. But anyway, how would we do this in practice? The waste plastics are added via an auger, for instance, to the pyrolysis chamber or onto the top of the molten metal where the material pyrolyzes. The vapors together with the solids are removed from the surface of the molten metal. The solids are separated from the gases are condensed to waxes and or oil. The pyrolysis chamber itself is from the hot dip galvanizing industry and can indeed be very large as shown in this picture here. But this is where I want to get to. How do the economics of mixed plastic waste pyrolysis, how do they actually stack up? Recently, we have published this paper. It is about a study of a mixed plastic waste pyrolysis plant located in Belgium. The general premise of this economic assessment is be conservative with the financial assessment. Choose the cost that makes the economic return more challenging. This is, of course, more of an art than a science. These here are the yield assumptions. The pyrolysis oil yield was set as 65%, which is quite low. We could have set it at nearly 80%. And we know that our process is an extremely good, has an extremely good performance in yield. Okay, and this is how the pyrolysis oil from tire pyrolysis from a rotary kiln looks like, a brownish or black liquid. But this is not what we saw. We saw this here. Our oil had waxes in the pyrolysis oil. This is significant, a clear indicator that our process is extremely fast. In other words, our reactor is close to the optimum in performance. A very important figure is to estimate the revenue that an operator may achieve for the pyrolysis oil. Here we made another conservative assumption. Instead of using the price of diesel, we used heavy fuel oil. But how do you set the price for heavy fuel oil when the crude oil price varies as much as shown here? We simply took the figure from February 2016 when the oil price was extremely low. That gave us a pyrolysis oil price of 210 euros a ton. This would be the revenue a plastic waste pyrolysis operator will achieve selling it to an oil refinery. This cost already includes the transport cost of getting it to the oil refinery. Waxes may actually achieve a higher price, but again, we just ignore this. A plastic waste operator will also achieve a fee from accepting the waste in the first place, the so-called tipping fee. We settled on 25 euros a ton. This is very low. Actually, it's too low, really. But let's go with it. This graphic here shows the cash flow. It assumes that the char or carbon gets disposed of at a cost of 130 euros a ton. There are also other costs, such as, the building of the plant, insurance, personnel costs, electricity, and so forth. So you would have to all estimate that. Taking the cost of the facility as 26 million euros, allowing for finance cost, inflation, and operating costs of some 800,000 euros per year, the internal rate of return, or IRR, calculates to 21%. This is a very good figure, considering that incinerators have been built with returns of less than 7%. The throughput of 40,000 tons a year sounds high, but actually it is not at all. In fact, in the US, for example, a competitor recently announced a planned 120,000 ton a year plastic pyrolysis plant. The financial returns, or the IRR, are sensitive to a number of factors. For instance, increasing the throughput of the plant to 50,000 tons a year increases the IRR to nearly 60%. Or getting an increased revenue for the oil increases the IRR also dramatically. Likewise, increasing the tipping fee to a more realistic 45 or 50 is probably even better, from 20 euros increases the IRR to 45%. Now, on a worldwide basis, we believe that some 100 plants are needed. In other words, this is a very large market. Moving on to a more classic composite waste. Here, glass fiber wind turbine blades. These things, for instance, are not recycled. This is what happens to them. They are landfilled. Now, is this good or bad? Well, I don't really know. This here is another waste stream that is not recycled. Aluminium laminated plastics, often used for coffee packaging and other foodstuffs, as shown here. Aluminium laminated plastic is an aluminium foil coated with plastic, typically polyethylene, on both sides. This is an excellent material for foodstuffs, but difficult to recycle. It is possible to use hydrometallurgical methods that would be acid or caustic to dissolve the aluminium and somehow afterwards then getting it back. But clearly this is a very expensive solution. Pyrolysis appears to be a better solution. The following will happen at 450 degrees Celsius. Nearly all the polypropylene converts into waxes. Little oil, some gases and carbon, and then of course aluminium. For pyrolysis, there are three options. Microwave pyrolysis is offered by a number of startup companies. Well, to me, that sounds rather like an expensive way of recycling a waste stream, using high tech to treat a low cost waste stream. Option B then would be the rotary kiln. Pyral is, for instance, operates a pyrolysis plant, a rotary kiln in Germany. So therefore, this waste can be loaded into a kiln, processed and unloaded from it. This waste stream could also be treated in our molten metal reactor rather than with a rotary kiln. But there is a problem. The economics of aluminium laminate recycling do not work out. And the technology used for recycling the waste is irrelevant for this problem statement. The problem is that economics of scale are not available. You simply cannot get enough aluminium laminate plastics into one spot. Luckily, there is help at hand. To make the economics work, the tipping fee has to be increased. This is what's called extended user responsibility. In essence, the producer of the product pays the recycler a fee to recycle these goods. From a waste recycler point of view, this may actually be a good thing, as this fee is not subject to market fluctuations like the oil price is, and therefore it is a steady source of income. Now, the Irish case is interesting and very tricky at the same time. Ireland's population is small compared to other states, and as a result, the waste volumes are low, making economics of scale even more difficult. Moreover, shipping costs across seas, may be prohibitive. So, in nearly every case, extended user responsibility may have to come into play. In summary, the advantages of our molten metal reactor are: we can treat different wastes with the same process, or even simultaneously. For instance, the aluminium laminated waste stream doesn't necessarily need to be 100% pure. There could be other plastics in this. We don't really care. Scale up is easy. Doubling the surface area of the molten metal doubles throughput. The reactor is extremely fast. The reaction temperature is constant throughout. Therefore, the product quality is very good and repeatable. The capex is low. The reactor is based on a mature industry, i.e. the hot dip galvanizing industry, and it contains no moving parts, i.e. the reactor is not rotating itself. Currently, we are part of a European research project into the recycling of composite wastes. These research projects tend to be large with many members and subcontractors as shown here. Over the next couple of months, we will be announcing new ways of how to recycle many composite plastics, such as the ones listed here. So, well, stay tuned, so to speak. The next step in the development of the technology is the demonstrator scale, just prior to commercialization. So yes, we are looking for funding. Thank you.
Very good. Thank you, Frank. And
thanks.
We'll move on to Gavin now for the next talk. And as I said, we'll have questions at the end, and we'll be using the Q&A for the questions at that stage. Okay. On you go, Gavin.
Thanks, Killian. You can see my screen all right, yeah?
Not yet. Not yet, Gavin.
Oh, sorry. Oh, apologies.
It's coming up now. Yeah.
Okay,
yeah,
thanks.
Perfect.
Sorry, there are 2 seconds. Good evening, everyone. It's a great honor to present you tonight to talk about my company and about the benefits that the maturing technology of waste pyrolysis can give to this planet. With human population set to increase from 7 billion to 9.7 billion by 2050, and combined with this, there will be the most rapid growth in human history from the lower to the middle and upper classes. While this is fantastic news, it is going to place huge demands on our planet to be able to supply the resources required. With this huge growth in consumption, inevitably that results in huge increase we as humans produce. It is not commonly known that waste is a huge contributor to global warming, with 1 ton of rubbish emitting 6.2 tons of carbon dioxide equivalent in the form of methane to the atmosphere. With the huge increase in demand for resources and the harmful effects of waste we as humans produce, it is now more important than ever for us to move away from our current consumption model of take, make, and dispose to a circular economy where we will continue to reuse resources by recycling. With this problem of what to do with all this waste has led many people asking simply why we do not just burn or incinerate our waste and use it to produce electricity from this waste. Although this may seem like a simple solution and reduce the fossil fuel consumption for energy production, it has serious long-term effects as it produces numerous harmful emissions and a very toxic ash, and unfortunately is extremely energy inefficient. So what is the solution? Pyrolysis, or chemical recycling, as it sometimes is referred to. Unlike incineration, there is no harmful or toxic ashes, and also there is no harmful emissions like dioxins or furans. This is for the simple reason, as Frank explained, pyrolysis, unlike combustion or incineration, there is no oxygen present, and this, as the name implies, dioxins contain oxygen molecules. As a general rule, oxygen-containing emissions are the most harmful to human health because we as humans absorb oxygen through our blood to breathe. A point I have to make tonight is that as many of you may have heard over the Christmas period, 2 peat-powered electricity generation stations have closed at Shannonbridge in Offaly and Lanesborough in County Longford. These 2 relatively new power plants, costing in the region of €250 million each, are a huge waste of taxpayers' money, and more importantly, will destroy their rural communities. Although we think of peat as being a very Irish resource, this is not the case, and is very common in Scandinavian countries. These Scandinavian countries, who also had to reduce the burning of peat to meet their carbon emissions, instead of taking the easy way out and just shutting them down, they decided to turn to the technologies of gasification and pyrolysis to install these plants next to their old peat-powered stations, which converts waste into a clean gas that fueled their power plant, thus stopping the closure of the plant, saving jobs and taxpayers' money, and more importantly, stopping the burning of peat and coal and reducing their CO2 emissions. As we can see here, sorry, apologies. Here is a picture of the power plant. As we can see, the new waste to gas plant tying into the existing power plant. Converting waste into energy using pyrolysis, although is an extremely useful technology, it can be put to far greater use other than producing electricity. It can be used to create highly valuable oils, chemicals, and other fuels, which has the ability to solve some of the main blind spots highlighted by the international energy agencies, which are petrochemicals, long-haul trucks and lorries, and the manufacture of materials like steel and plastic. Of all the materials that we can produce, that we can process by plastic pyrolysis, by far the most lucrative and readily available, and as we are all well aware, is the most pressing environmental issue of our generation. The biggest growth of any type of human waste by type will be plastic. By 2050, plastic production is set to quadruple, and there will be more plastic in our oceans than fish. I will draw your attention to the plastic share of global oil consumption, which will be increasing from 6% to 20%, and its share of the carbon budget will increase from 1 to 15%. We will later discuss how pyrolysis can drastically reduce both of these. I'm not going to go into detail in this lecture about the current plastic crisis, as it has been well publicized, and I want to spend the rest of this presentation discussing the only, and I mean the only, solution to the plastic waste crisis, which is the pyrolysis of plastic waste, or chemical recycling, as it is sometimes referred to. I am calling this a plastic waste crisis because we do not have a plastic crisis, we have a plastic waste crisis. The reason I say this is because plastic is one of the most critical materials in the fight against climate change. It reduces food waste, reduces the weight of cars and planes, thus reducing fuel consumption and making electric vehicles possible. Most materials, when compared to plastic, have a far higher CO2 equivalent when viewing it over the life cycle of the product. This is because of how light plastic is per unit strength, thus requiring less of it to be required and for it to be lighter for it to be transported. The issue we have is that we have not found a way to recycle plastic efficiently. The same way we have other materials like glass and aluminium. The reason for this, although there is only 7 resin codes, there are actually thousands of different types of plastic. Different combinations of dyes and additives can be added to the basic resin to produce a desired color, shape, and texture in the final product. These variations in manufacturing process lead to different melting points and other properties within the same resins code. So in order to mechanically recycle plastic, it has to be separated into the correct type, color, production method, be relatively clean and of good quality. And this all has to be done while waste companies are trying to make a profit. Along with this, every time plastic is mechanically recycled, its quality degrades. This is the reason 80% of plastic that has been recycled once end up in landfill or incineration. In most communities, only bottles with necks marked with resin codes 1 or 2, which are soda bottles and milk jugs, are recycled. Containers without necks, such as tubs and trays and plastic films, are not easily recyclable. Even if they are marked with the same resins codes as their bottle counterparts, this is because plastic bottles are blow molded while plastic tubs are injection molded. The different additives used in each process means that the two cannot be mixed during recycling. So a way to recycle mixed type, mixed color with no additives, dirty and poor quality plastic, where it can be recycled infinitively without its quality degrading, and most importantly, making it profitable. The only technology that can do this is plastic pyrolysis. I just also want to make the point that plastic pyrolysis will not take good quality plastic waste destined for mechanical recycling. As Frank said earlier, we will have to pay for this feedstock versus getting paid a gate fee by waste companies to accept this previously unrecycled plastic waste, as they are trying to avoid high landfill and incineration costs. A facility to recycle this unrecyclable plastic, like plastic films, is badly needed for waste companies who want to avoid the high costs associated with landfill and incineration. Currently, the likes of your Pandas, your Country Cleans, etc., have separated plastic in their facilities, like the picture shown, with no market to sell this valuable material into. A point I would like everyone to leave with today is that biodegradable plastics are not the answer to the plastic crisis, and in fact are making the crisis worse. If anything, we should be reducing the types of plastic that we use. As I said earlier, if you throw biodegradable plastic into your general waste bin and it ends up in the landfill or into the environment or in the ocean, it will behave the exact same as any other type of plastic and will take just as long to degrade. Only industrial composting facilities, not your compost bin at home, can degrade this plastic as high temperatures are needed. What is worse is that very few of these industrial composting facilities accept large quantities of this plastic waste. If a biodegradable plastic ends up going to incineration, which is very possible, it will break back down into what it was formed by, which with bioplastics is often acids, which obviously is a very bad pollutant. I now want to turn to a mistake that was made over 15 years ago, which I am worried we will make again in the coming years. In 2008, drove by high oil prices and a desire to lower the world's emission, 10 billion tons of biofuel in the form of ethanol was made. 45% of it coming from Brazilian sugarcane, 45% of it from American corn, and the remaining 10% from around the world. In the same year, the EU produced 1 billion tons of biodiesel from rapeseed. This accounted for 5% of the world's cropland, being changed from food to biofuel production. This was a key factor that caused the world food supply to dip below world food demand in 2008, which resulted in food riots across the world and countless deaths due to malnutrition. This madness was thankfully reduced, but unfortunately, traders who are seeking higher profits are now eyeing up the bioplastics market to once again take food that should be used to feed people to produce these bioplastics. This is causing rainforests to be cleared to make way for palm oil, to produce compostable plastics, to make us in the West not feel guilty about our disposable coffee lids. And with 1 billion people going to bed hungry tonight, this is, in my opinion, close to a crime against humanity. Even with this, there is still a future for biofuels as the technology is evolving. And second generation biofuel plants are coming online, which can provide biofuels from waste. Pyrolysis is one of the key technologies being used to enable biofuels to be produced from agricultural wastes and forest residues. This is providing a sustainable and ethical way of producing this fuel. Polyolefinic plastic, which is low-density polyethylene, polypropylene, and high-density polyethylene, which accounts for 60 to 70% of the world's plastic, and more importantly, the hardest plastic to recycle, used in the production of plastic films and pots, tubs, and trays. With this plastic, it is very possible to produce the highest quality chemicals and oils, which can be used to make virgin quality plastics by great companies like BASF. The solution to the waste plastic crisis and to get recycling rates above 95% is to turn previously unrecycled plastics not back into plastics, but into its feedstock, oil. This oil can be used to produce virgin quality plastics. This will drastically reduce the CO2 footprint of plastic production. Combined with this, the third generation of plastic pyrolysis plants, which hopefully our company will start designing in the next 3 years, will reduce carbon dioxide emissions by around 65% by converting plastic into its original monomers. I will not go to this today due to time constraints, but it is clear to see the potential that plastic pyrolysis has. The development of this industry will give waste plastic a value similar to aluminium cans. This will create a natural industry for the collection of plastic in countries without developed waste infrastructures, and will give employment to the world's poorest and where it is most needed. The global outrage about the plastic waste crisis has driven consumer brands like Nestle, Pepsi, and Unilever, who are aiming for 100, 33, and 25% respectively of their materials to be produced from recycled content by 2025. Coca-Cola are aiming for 50% recycled content by 2030. How, you might ask, are Nestle going to achieve 100% recycled content by 2025 while requiring food-grade quality plastic? You guessed it, by investing in their very own plastic pyrolysis plants. The EU has also doubled the plastic recycling rate from 22.5% to 50% by 2025. Countries like Ireland are going to find it hard to hit this target without investing in plastic pyrolysis plants. In turn, this demand has placed huge pressure on petrochemical companies to produce plastic from oil derived from waste plastic, which has led to a €300 per tonne premium on pyrolysis oil over oils derived from fossil fuel sources. This is a phenomenal premium, which is creating a gold rush in the plastics pyrolysis industry. This has led to companies setting up, buying old first-generation pyrolysis plants and technology, which has failed before. And when companies like ourselves and other second-generation pyrolysis plants come online, these unfortunately will fail again, as the law of supply and demand will once again decrease the value of this oil. Nearly all of the current plastic pyrolysis companies on the market are using failed first-generation pyrolysis plants. With their extremely high operating and capital costs, unfortunately, they will be forced to close once again. So let me introduce my company, Pyro Plastic Recycling Technologies, whose mission statement is simple: to eliminate all plastic waste by the year 2040. Although people may laugh, this is an easily achievable target. By increasing our mechanical recycling rates and by investing in technologies like plastic pyrolysis, which we believe is the missing jigsaw piece to eliminate plastic waste. So a bit of background on myself and how I suppose I became obsessed with plastic pyrolysis. So my first project out of college was a plastic pyrolysis plant over 10 years ago. This gave me an early insight into the problems encountered with plastic recycling, and I was shown the simple process of heating plastic in the absence of oxygen to 400 degrees and cooling it back down to 10 degrees, and you will get a beautiful oil. I found this amazing and went on to make my own smaller plastic pyrolysis plant in my garage back home. But the real thing that drove my obsession was being on site and coming to the realization that nearly as much fuel trucks were bringing fuel into the plant than were leaving the plant. I was shocked at this discovery, and when I tried to raise the issue, and I suppose being a kind of young fellow out of college, I was told to shut up and just build the plant. But after doing some research, I found out that the biggest criticism of plastic pyrolysis is that it consumes more fuel than it produces. I knew this wasn't right, and when I started to investigate this, I found out that only 5% of the fuels produced can fuel the heat of reaction. This figure includes for heat loss. This led me to design a plastic pyrolysis process that is over 40% more energy efficient than established pyrolysis companies on the market. The purpose of this first project, of my first project, was to take an existing plastic pyrolysis plant and upgrade it to produce diesel that could meet the EN 590 standard so that it could be put directly into cars or vehicles. Unfortunately, this failed miserably due to two main factors. One, a fundamental misunderstanding of the chemical reaction occurring, leading to an oil with a high olefin content and thus transport fuel not being the correct market for it to be sold into. But more importantly, it contained a high level of contamination, which is of course to be expected when dealing with a waste product. The problem is, if contamination enters the process, it will end up in the product oils, making it not meet the very stringent standards set by the markets, like the petrochemical industry. This led me to come up with a method to remove contamination mid-process after it enters the process, so it does not end up in the product oil. It is especially good at removing the main contaminants that cause oil not to meet the stringent standards. This is another factor that is critical to the success of plastic pyrolysis and can enable products to get a higher price on the market. My next project out of college was another plastic pyrolysis plant based in the States, which tried to solve the next major criticism of plastic pyrolysis, that this technology cannot scale. This project aimed to produce 60 tons of plastic a day with one reactor, thus breaking the 500 kilogram per hour limit of the plastic pyrolysis reactor. This again failed miserably due to the direct versus indirect heating methods that Frank discussed earlier. All of these first generation plastic pyrolysis plants went on to fail because of poor technology, which was unable to cope with the fluctuating crude oil prices because of high operating and capital costs. This was a great start for a young engineer getting first-hand experience of the main criticisms of pyrolysis, of the three main criticisms of pyrolysis. As I went on to work in other industries, I always kept plastic pyrolysis in mind when I saw how other industries dealt with these three main issues encountered by plastic pyrolysis. In 2017, when China stopped importing the world's plastic waste, I left my job to provide consultancy to the new plastic pyrolysis companies that were setting up. When I saw how the industry had changed from paying €100 per ton for waste plastic feedstocks to receiving €200 tons in a gate fee to accept this waste, and sitting across the table from oil companies who were offering huge premiums for pyrolysis oil when crude oil prices were at rock bottom, I decided it was perfect timing to bring my process to market. One important point I want to talk about is how critical economies of scale is. Plastic pyrolysis, like plastic production, operates on the principle of economies of scale. That is, that as you increase throughput, your cost per unit throughput decreases, and correspondingly, your profit per unit throughput increases. As Frank outlined earlier, because of heat transfer, direct versus indirect, and plastic being a very poor conductor of heat, first generation plastic pyrolysis reactors fail to scale above 500 kilograms an hour. This is quite a problem when the size of your market is 100 million tons per day. Because of this 500 kilogram per hour limit and the inability to scale, this has driven first generation plants to simply copy and paste their process under the same roof in order to scale. As we can see from the 3D model of a proposed plastic pyrolysis plant located in Germany, with each white box being a reactor, a total of 16 reactors. And this company is planning a plastic pyrolysis plant in Belgium with 20 number reactors. This is not taking advantage of the economies of scale and is not sustainable. Pyro decided to reimagine existing technologies from the oil and energy sectors that have been proven to work at huge scale and that have many huge benefits, which is why it is the technology of choice in the industry for cracking of long-chain hydrocarbons. This piece of technology is called a fluidized catalytic cracker. Unfortunately, the problem we at Pyro faced was that there has been many attempts to process plastic using this technology, which unfortunately have failed. This is because plastic behaves completely differently to any other feedstocks that have been supplied to these crackers in the past. Pyro have found a way to manipulate this plastic in order for this reactor to process it. We believe that this breakthrough is the key to being able to produce huge quantities, to be able to process huge quantities of plastic waste and to solve the current plastic crisis. What's next for our company? Pyro have taken the approach of partnering with multinational companies with manufacturing power and the economic might to roll out our technology on a large scale, enabling our process to have a huge impact on the global plastic crisis. Pyro have designed their first plant with this in mind, and as it is of modular design, we'll be able to copy it and ship this plant all over the world. I will leave you with an old Greek proverb. A society grows great when all men plant trees whose shade they know they shall never sit in. What does that say for our society, who discard 350 million tons of waste plastic every year, leaving it for the next 16 generations to deal with? Thank you so much for listening tonight.
Thank you, Gavin, and thanks to Frank as well. We have a couple of questions there, so we might have a look at some of the questions there. We've got a few questions there. First one, we have a Leon there. For a 40,000 ton per annum plant, what would the footprint be, Gavin?
I estimate approximately about 3 acres. Would you agree with that, Frank?
I've no idea right now.
Typically, you need 1 acre, a kind of 1 acre covered, shall we say, 2 acres uncovered. For that kind of throughput, yeah, that's 40,000 tons. It will be around the 3 acre mark. Obviously, you can store plastic off-site and maybe transport it in if you're stuck with footprint.
Okay, and another question out there. Can the energy be recovered that is used to melt the plastic? So what sort of rate of energy recovery would you have? I know you've been looking at that. So
I suppose our process uses a heat exchange. So as I said, plastic pyrolysis is a very simple reaction. You take plastic in the absence of oxygen, you heat it to 400 degrees, and you cool it back down to 10 degrees. Our process uses a heat exchange where the products from the pyrolysis reaction, the hydrocarbon vapors, are used to heat the incoming plastic. Again, I suppose that's one of the many reasons why we're able to have such an energy efficient plant. And along with that, we actually capture pretty much all of the waste heat, and we convert this to electricity, which reduces our electricity bill by half using an organic Rankine cycle, which is a kind of, even though it's been around a while, it's really coming into prominence of late.
And are there any existing plants in Ireland?
Yes. So I suppose Sinar was eventually set up in Portlaoise in back it was about 10 years ago. Unfortunately, that failed as discussed. But hopefully more plants will be coming online.
And okay, is there any key control challenges to the run continuously batch, or what are the key control challenges? Any thoughts?
Yes, batch is absolutely horrific. I assume you agree with me on that, Frank.
Oh God, yeah.
The problem with batch reactors, right? So you take plastic, you're being batch, you have to fill a vessel. At the start, you get no hydrocarbon flow. It comes up to a maximum hydrocarbon flow and it goes back down to zero again. So you have to size your plant for the maximum flow. This is also incredibly hard to control. By using a continuous pyrolysis process, it's much easier to control, and I suppose process variations, I suppose they just don't vary that much. Nowhere near what batch does, and neither myself or Frank have batch processes. So yeah.
And presumably energy recovery is much easier with continuous compared to batch.
Absolutely. Like it's it's one of the many reasons why their operating costs are so high, their capital costs are so high, and again it just takes options like heat recovery, making electricity from waste heat, removes everything like that.
What are the key safety considerations for a second generation pyrolysis plant?
So I suppose they're just as safe as a first generation pyrolysis plant. So just to explain to everyone, the difference between a first generation pyrolysis plant and a second generation pyrolysis plant is that a pyrolysis plant, that the reactor can scale above 500 kilograms an hour. There should be no real different safety considerations between the first and the second generation pyrolysis plant. The only difference is, instead of copying and to be able to do big throughputs and copy and pasting 500 kilogram reactors, you'll have one big reactor that will do your plant's total throughput.
But presumably, I presume you have a lot of flammable material at very high temperatures, and the bigger the plant,
yes,
more you have.
absolutely. Look, once the hydrocarbon vapors are produced in the pyrolysis reactor, it's no different to an oil refinery. Look, like it goes without saying, safety, safety has to be engineered in. Yes, everything's flammable, everything's dangerous, but I suppose that's what us engineers are here for.
And are there any waste products from these processes, and what happens to them?
Yes, there is a small quantity of ash, kind of an ash being produced. So again, it's like pyrolysis is so varied, but I'll just talk about. I suppose I'll talk about my process. That is, as I said in the presentation, there is processing polyolefin plastic. The amount of ash is, for every ton, there is approximately, again, like there's a lot of factors, is approximately 150 kilograms, which is incredibly low. And unlike incineration, as I said in my presentation, this is not toxic. It is not toxic. Like it is, you cannot compare it to incineration. No way. It can be, like, the ash can actually be sold to for roads, etc. Obviously, there is emissions, as in, like, obviously you need fuels to heat the pyrolysis reactors. So when you pyrolyze polyolefin plastics, you actually get incredibly clean, an incredibly clean fuel. So polyolefin plastics only contain carbon and hydrogen. They are much cleaner than crude oil, which contains sulfur, chlorine, a whole list of contaminants. You do not get that with polyolefin plastics. You just have carbon and hydrogen. The gas it produces is incredibly clean, and as we all hear, I suppose another kind of technology that's taken off is the hydrogen technology, with green hydrogen being produced. The gas, which is called syngas, produced has a very high hydrogen content. So that when it's burnt, all it emits is water vapor.
Yeah.
Yes.
Another question there: are there any odor issues associated with the off gases and with the plant?
No. No, not with the plant. With like, again, the beauty of plastic pyrolysis, we can take the worst plastic. Our listeners are very familiar with anaerobic digestion. We can take clean plastic from anaerobic digestion. Obviously, that's going to smell. But we can also take clean plastic that's used in, like, pallet wrap. So again, it's a case by case basis on the plant. But the actual pyrolysis part of it, there's actually no real smell, no worse than any other kind of industrial plant.
Frank, I think this next one is for you. Is the process suitable for rubber materials? Maybe you might answer that one, Frank.
Yes, it is. We have actually done this. We are recycling tires with our process. So, and in fact, there then you have carbon black coming out, which is, 30% of a tire is actually carbon black, which is nothing else but, well, it's not char, but it's carbon. So, and this is a very expensive material, which we actually do want to recover. So we're doing everything to recover that. All right. So in that sense, there's even less waste than anywhere else,
Frank has a process where tires are put into molten zinc and they under a nitrogen atmosphere with pyrolysis. And you've done some pilot work in that, haven't you, Frank?
Yes, or more than that. But yeah, that's developed. That's in development at the moment. So but it's not part of this presentation. That's a different process. Okay.
Now, I think we answered the next one. And are there any contaminants in the waste raw materials that cause significant issues, such as glass or metals or anything like that?
Glass is okay for my process.
Mm-hmm.
Metals would be okay too. But,
mm-hmm.
You wouldn't want to put mercury in there or anything like that. But generally, it's not an issue. In the tire, there's steel in it. There's a bit of copper in it, and we don't really care. All right. In fact, we're dealing with the steel content of the tire. All right. So yeah, it's not an issue, generally speaking.
We're the same as steel and plastic actually don't they don't melt at the temperatures we're at. It simply just gets caught in a filter before it enters the pyrolysis reactor. So it's fine.
And how do you generate the heat? Presumably, once you get up to 400 degrees, we're looking at electricity or something, are we? Or how do you get the high temperatures?
So I suppose we're producing a syngas the whole time. It's one of the products of the process. that is recycled back to burners that heat the. So it's self-sustaining. You know, maybe the very first time we start to think up, we're obviously going to have to bring in natural gas or something like that. But after that, I suppose the plan is that it's completely self-sustaining. And we're actually so energy efficient that we're sending excess syngas for electricity production.
Yeah,
And
we're the same. There's no difference.
And are there grants available in the EU for potential plans?
In theory, yes. In practice, I don't know.
I was just about to say, yeah.
Yeah, I think you would get some grants. Yes. All right.
Okay, I think we've come to the. I think we've answered everybody's question there. So if that's all right, I'll call on Pat Kennedy of the IChemE to give us the vote of thanks. Pat, if you're ready to go.
I'd love to, Killian. I'm very impressed, I have to say, by, well, Gavin, of course, is CIT graduate, so it's not any surprise that he's that impressive. And of course, I've worked with Frank over the years as well, so there's no surprise there either. But I am impressed by the two very knowledgeable presenters setting out both of their processes in clear, very understandable language and diagrams, and that very thought-provoking in both, and particularly Gavin, taking a swipe at the bioethanol, and rightly so, industries. That might be worth following up on a different level, but it's great to see practitioners like Killian and I. We stand in lecture halls theorizing to a great extent. We try and bring practical aspects into it, but it's great to see two men who are steeped in the practicalities of these things, sharing their knowledge with ourselves and our students, of course, as well. So just a thought, Killian, in years to come, you might be organizing school tour or class tours to some of these plants. I'm sure it'll be very interesting for our students as well. So thanks, gentlemen. Well done. Thanks very much.
Thank you.
Thank you.